At the end of the 19th century, physicists really thought they had it all figured out. But then, one simple glowing object led their best theories to predict infinite energy. A prediction so spectacularly wrong, it didn't just bend the rules, it broke reality as they knew it. This is the story of that beautiful failure. I mean, just try to put yourself in their shoes. You've got Newton's laws running the planets like clockwork. You've got Maxwell's equations describing light perfectly. It really feels like you're just putting the finishing touches on a complete theory of everything. So you go to tackle what seems like a pretty basic question, the glow of a hot object, right? Whether it's a piece of metal in a forge or the sun itself. A complete theory of physics should nail this, no problem. Well, what they found was about to shake science to its absolute core. So here's how we're going to walk through this story. First, we'll look at the elegant puzzle that classical physics set up. Then, we'll see how that puzzle became a recipe for absolute disaster and witness the catastrophe that blew everything up. After that, we'll meet Max Planck and his desperate idea, which kicked off nothing less than the quantum revolution. Okay, so how did the best minds of the time even begin to tackle this? Well, they did what physicists always do. They simplified the problem. They came up with a perfect, idealized object to figure out how things radiate light and heat. They called this thing a black body. And really, the best way to picture it is as a perfect, theoretical oven with a tiny peephole. The walls are at a steady temperature, and the atoms inside are jiggling around, spitting out light. That light bounces around, getting absorbed and re-emitted over and over, until the whole thing reaches a perfect thermal balance. The whole challenge was to predict the spectrum of light you'd see coming out of that peephole. And the classical approach to this was just beautifully logical. They broke it down into two pretty straightforward questions. First step, just count them up. How many possible ways can light waves, or modes, exist inside that box? Second step, figure out the average energy of each one of those waves. Multiply the two, and boom, you should have your answer. Simple, right? Answering that first question is basically just geometry. Think about it for a second. Inside a box, you can only fit so many long, low-frequency waves. But when you get to short, high-frequency waves, you can pack an absolutely insane number of them in there. And the physics gives us this exact formula for it, which shows that the number of available slots for waves just skyrockets with the square of the frequency. So more frequency means way, way more possibilities. So what about the second question, the energy part? For this, physicists pulled out one of the crown jewels of their science, the equipartition theorem. It's this really democratic idea. It basically says that when a system is in thermal balance, energy gets shared out equally among all the possible ways it can be stored. So every single wave, it doesn't matter if it's high or low frequency, gets the exact same slice of the energy pie, an amount that just depends on the temperature. All right, so we've got our two perfect classical answers, the number of ways for light to exist, which skyrockets with frequency, and the average energy for each of those ways, which is the same for all of them. So let's just put them together. What could possibly go wrong? And this is what you get, the Rayleigh-Jeans law. You just multiply the number of modes by the average energy per mode. I mean, this thing was built from the absolute bedrock of 19th century physics, Maxwell's electromagnetism, Boltzmann's statistics. I mean, this thing should have been a massive triumph. Instead, it was an unmitigated disaster. Now, here's the crazy part. For low frequencies, down in the infrared and radio wave part of the spectrum, the law was perfect. It matched experimental results beautifully. But as scientists started looking at higher and higher frequencies, pushing up towards visible light and then ultraviolet, the prediction didn't just drift off course, it went completely off the rails. And this is the moment where the theory doesn't just stumble, it completely faceplants, leading to a prediction that isn't just wrong, it's physically impossible. This spectacular failure got a very dramatic name, the ultraviolet catastrophe. And that's because that frequency squared term in the formula means that as you go to higher and higher frequencies, into the ultraviolet and beyond, the predicted energy doesn't just get big, it shoots off toward infinity. This meant that any warm object, your cup of tea, a lump of coal, the sun, should be blasting out an infinite amount of energy, mostly as gamma rays. Which, last I checked, they don't. And you really can't overstate how bad this was. This wasn't just some rounding error. The theory was literally predicting that heat could spontaneously flow from a cold object to a hot one. That is a flagrant violation of the second law of thermodynamics, which is about as sacred as it gets in physics. The entire beautiful cathedral of classical physics had a massive, fatal crack running right through its foundation. So the situation was just dire. Physics was broken. And into this crisis steps the German physicist Max Planck, who comes up with a solution so bizarre, so completely out of left field that he barely even believed it himself. And those are his own words. Planck later said his own idea was an act of desperation. He wasn't trying to start a revolution. He was a conservative guy, just trying to fudge the math to make the formula work. But to do it, he had to question an assumption so deep, so fundamental, that no one had ever thought to question it before. For centuries, everyone just assumed energy was like water, a smooth, continuous fluid. You could always have half as much or a quarter as much, on and on forever. Planck's desperate idea was to suggest that maybe, just maybe, energy is more like money. It's lumpy. It comes in discrete packets, or quanta. And you can't have a fraction of a packet, any more than you could have half a cent. And here was the killer move. Planck proposed that the size of one of these energy packets, the value of one of these coins, was directly proportional to the frequency of the light. Higher frequency meant a bigger, more expensive chunk of energy. And the exchange rate between frequency and energy was a brand new fundamental constant of the universe, a number we now call h, or Planck's constant. And this one simple, weird change fixed absolutely everything. But how? Well, think about it. At low frequencies, the energy packets are tiny and cheap, so there's plenty of energy to go around, and things behave just like the old classical theory. But at high frequencies, the price of a single energy packet becomes enormous, way more than the typical thermal energy that's available. It's like trying to buy a Ferrari with a loose change in your pocket. It's not going to happen. The high-frequency modes are simply too expensive to ever get activated. They get frozen out. And what started as Planck's desperate mathematical trick didn't just solve one annoying little problem. It unknowingly blew the doors open to an entirely new and much weirder understanding of the universe. So Planck took the old formula for the number of modes, but he combined it with his new radical rule for quantized energy. And the new law he created, it wasn't just close. It was perfect. It matched the experimental data across the entire spectrum, taming that infinity and completely averting the catastrophe. And in doing so, he had accidentally written the very first equation of a brand new science, quantum mechanics. And the legacy of that discovery is, well, it's just staggering. The same core idea is used today to measure the temperature of a star billions of light years away, just by looking at its color. It's essential to understanding the faint afterglow of the Big Bang itself. It explains weird things about how solids hold heat, and even describes the noise in sensitive electronics. It even shows up in the physics of how black holes might evaporate. So, what does this all mean for you? Well, the next time you preheat your oven, just take a second and remember this. If the universe were purely classical, that glowing red heating element would be an absolute death ray, spewing out an infinite torrent of gamma radiation. The simple, boring, stable fact that it just gently warms up your dinner is direct, everyday proof that our universe is, at its very core, quantum. You see, the ultraviolet catastrophe wasn't really a disaster in the end. It was a signpost. It was a beautiful failure that forced physics to kick and scream its way out of a comfortable reality and into a much stranger and, frankly, far more interesting one. Which really just leaves you with one last question. What other comfortable assumptions that we hold today are just waiting for the right experiment to come along and break them, revealing a whole new layer of reality we haven't even begun to dream of yet?